Okay, these next couple of lessons are meant to be fairly short and sweet, so I'm going to keep them concise here, but if you do need more on this content, you can certainly ask for it in class. We will be expanding as necessary. As you see at the top here of section 6.4, we're working on midpoints of a triangle, and this is a mid-segment that is a concept that you have seen before. So just kind of revisiting in the sense of creating a quadrilateral that has certain properties. So when you take a midpoint of any side of a triangle connected to another one, you form a midsegment, and that's what segment ED is here in this diagram. And part A, it's asking us to use the midpoint formula to locate those points. So I've done that. You could also use slope however you want to locate those midpoints. But they've been located at 3, 7 and negative 5, 1. So point E is the one at negative 5, 1, and point D is the one up here at 3, 7. All right, so take a minute to do that. And then when we connect segment point E to point D and create segment DE, we can then do several things with that segment. We can determine the slope, we can determine the length, and compare it to the one that is presumably parallel to it. And so by doing the slope and coming up with the same exact slope for DE as we do for BC, we have shown that those two segments are in fact parallel. And by doing the length of them, we can also see another relationship, which is that the midsegment is half the length of the original triangle segment. Now, the way to reason that is if you use midpoints here, what you're doing along these sides of the triangle, along AC and AB, is you're splitting it into a 2-to-1 ratio. So in other words, the full segment AC is twice as big as the half segment AE. So the other segment of the triangle should also be half as big as the segment of the outer triangle. So it makes sense in terms of dilating proportionally, but we've just shown it here anecdotally with this distance formula proof. All right, so the observation is that the segments are parallel and that the midpoint connector is half the length of the third side. So that mid segment is going to have those two properties every time we see one present. So in exercise 2, a triangle with side lengths of 10, 14, and 18 had the midpoints of all three sides connected by segments. And so the perimeter of the inner triangle is going to have, well, it's going to have segment lengths of half of those triangle segments, right? So the 10 would become a 5, and the 14 would become a 7, and the 18 would become a 9 for those segments that are parallel to the outside ones. So the perimeter total here is 21. The perimeter total of the original triangle was 42. So what we can say is if we have a triangle formed by midsegments, it will be half the perimeter of the original triangle because every segment is half of the one that it's across from. Okay, triangle LMN in exercise 3 has the vertices shown here. If the midpoints of sides LM and NM are connected with a segment, which of the following would be its slope? So to me, it makes sense to draw a diagram whenever one's not provided. So I drew triangle LMN. I put in the midpoints of LM and NM just to be able to see a little bit more clearly where that midsegment is running parallel to. And it's running parallel to segment LN. So because of that fact, I really want to know the slope of segment LN, where had I not drawn the diagram, it may not have been so obvious which one to calculate the slope of. So calculating the slope of LN using coordinate slope calculations gave me 5/2, and therefore the midsegment must also be a slope of 5/2. So just draw the diagram whenever there isn't one provided. It will definitely help to visualize. All right, on the next page, exercise 4, you're going to need to get your compass out. We have triangle ABC drawn to start with, and we are to extend segment DE through E, so on the other side of E, to point F, which is not drawn for you, so that DE and EF are the same length. So if you can attempt it with your compass before I explain how it's done, but give it a try and then come on back. All right, so if we need to use a compass to duplicate a segment length, what you might do is take your straight edge, lay it down on DE, and extend it out past E further than you think you might need to go. Then take your compass, put the metal point on E, and put the pencil point on D, so you have your radius established, and just turn it over, and then where the compass lands on the line is going to be point F, and that will be the same distance from E that D was. Okay, when you draw in segment BF in part B, we have a diagram that looks like this. So to give an argument for why AED, this top triangle, must be congruent to BEF, we need to look for equal angles or some other equal sides perhaps that will determine where we have enough to prove that those triangles are congruent. So one thing I noticed is that because these points were marked as midpoints, right? E and D were midpoints. I know that AE and EB are the same length, so those are congruent. I also know that DE and EF are the same length because my compass said so. So that's two pairs of equal sides. I have the angles between them because they're vertical angles, and so I have a side angle side congruence argument. So once those triangles are congruent, why does that show that BF, this segment out here, is parallel to AC? Well, typically when we want to prove things parallel, we want to look for alternate interior angles along a transversal. So because these two triangles are congruent, I can also say that angle FBE, which is down here where I'm pointing to, is going to be congruent to angle DAE up here. Right? Those are the corresponding angles. And because those corresponding angles are equal, now my lines are parallel. Okay, so if I follow transversal AB across the conjectured parallel lines FB and AC, the angles that would create parallel lines are in fact congruent because of the triangles, and so that allows me to say that the lines are parallel. And since CD falls on AC, we know that FB is also parallel to CD because that's just a portion of that segment. So why must BF and CD be the same length? Well, if D is the midpoint of AC, then these two segments are equal, AD and CD. And we knew that BF was equal to AD because of the triangles being congruent. So by substitution, we can say that BF is equal to CD. All right, so now why do we know it's a parallelogram? Well, the first thing we did was prove that these opposite sides were parallel. Now we have proven that those opposite sides were also congruent. And one of our previous proofs about parallelograms was that if two opposite sides are equal and parallel, then we have a parallelogram. So that's one way to show it. The other way to get into it is that the DE segment is going to be parallel to the CB segment because it's a midsegment, right? And once we show that it's a midsegment, now we have opposite parallel sides in both directions.